is a challenging task. Why? Because one has to review the foundation of Jacobi's theory in order to make it applicable to a dynamical system other than Hamiltonian system on a cotangent band. It is well known that Jacobi's theory is based on the theory of Hamilton-Jacobi equation. But nobody knows what is the Hamilton-Jacobi equation for Soliton equation, for the theory of partial differential equations, which is integrable. So you have to improve the theory of Jacobi. This means having to develop theory separation variables without using the Hamilton-Jacobi equation and its complete integrals. What is the complete integrals for the KdV equation, for example? Okay. So my main message today is that such kind of extension of the Jacobi theory is possible, that its roots were already in the original paper of Jacobi, 1838, and that Jacobi at that time had a kind of bifurcation. I had two possible routes to follow. The standard route or the route I will try to show you today. Unfortunately, in my opinion, I choose, in some sense, the wrong route because it's the route which has more assumptions at the beginning and so has a smaller field of applications. So that is the point. To arrive at the new formulation in the most straightforward way, I start from a notion that has been almost forgotten in textbooks of mechanics, but which was in Jacobi. My first contribution, the notion of Jacobi form of equation of motion. This means serious term. Jacobi forms of the equation of motion should be explained of a dynamical system. I have three contributions. My first contribution is then to revive this notion, showing that appropriately understood, just an improvement with respect to the original formulation of Jacobi, it provides a sufficiently broad basis for a general theory of separable system, which goes beyond the limits of the classical Hamiltonian approach. The second contribution is to show in a concrete example that the extended theory is useful for the study of Soliton equation. That is the reason of the title, the Jacobi form of Soliton equation. The third contribution, so to say, is a conjecture. I will formulate at the end of conjecture. The aim of the conjecture is to try to identify the theoretical reason which explain why the methods of the theory of separable system are effective in the study of Soliton equation. It's an interesting question. So, just to start, let me begin from Jacobi. My starting point is Jacobi. In order to frame the problem, it is useful to recall how the Jacobi form of the equation of motion was discovered. It was announced by Jacobi in a letter dated December 28, 1838, addressed to his colleague Arago in Paris. The letter said, this is an excerpt which I took from a paper of Perelomov. I have not looked carefully at the whole letter, but okay. Through the authority of Perelomov, that is correct. Monsieur, je suis parvenu à ramener au quadrature la ligne géodésique sur une ellipsoïde à trois axes inégaux. Ce sont des formules extrêmement simples, des intégrales abéliennes qui s'échangent dans les intégrales elliptiques connues en égalant entre deux de ces trois axes. Ces problèmes m'ayant paru longtemps très difficiles pour Jacobi. I will remark this fact. Très difficile. Je crois que sa solution pourra intéresser peut-être quelques-uns des illustres membres de l'Académie des sciences. So let's look at the solution of Jacobi. In the letter, Jacobi informed Arago that the newly developed theory of the Hamilton-Jacobi equation was just one hour after the discovery. And the use of the elliptic coordinates confocal to the ellipsoid allowed Jacobi to write the equations of motion of the geodesic flow in the particularly simple form written here. This form is reproduced from a famous treatise of mechanics, Appel traité de mécanique rationnelle. The coefficients U1, U2 are the elliptic coordinates, the dot is the time derivatives, and the coefficients A1, B1 are functions of the elliptic coordinates only, U1 only, and the coefficients A2, B2 are functions of the elliptic coordinates U2 only. These equations are the first example, I believe, of I cannot read that, sorry. I have to change. So, well, I believe the Jacobi form are the first example of the Jacobi form of the equations of motion of a Hamiltonian system, and also are one of the first examples of the process of separation of variables according to Jacobi preferred procedure. That means according to the theory of the Hamilton-Jacobi equation. I am interested in understanding in depth the meaning of the above equation. Very simple, but there is a structure, and I am interested in understanding the structure of these equations, challenging the widespread opinion that they are confined to Hamiltonian mechanics. I think that this view is too restrictive. I want to argue that the study of the geodesic flow on the ellipsoid performed by Jacobi is incomplete, and that only after its completion one can understand the true meaning of the equation written above. For this reason, I will now complete the study of the geodesic flow on the ellipsoid, taking advantage of information that was precluded to Jacobi. That is the reason he did complete the study. The new analysis we are allowed to see the above equation in a different light. The missing information in Jacobi treatment of the geodesic flow on the ellipsoid is that the flow has a second integral of motion, other than the energy H. Let us denote it by J, since it was discovered by the German geometer Joachim Stahl a few years after the work of Jacobi. Its existence gives us a more complex picture of the geometry of the cotangent bundle of the ellipsoid. Next to the Hamiltonian vector field X-ray describing the geodesic flow, I'm sorry. Let's start again. Describing the geodesic flow, we now have the Hamiltonian vector field Xj associated with the Joachim Stahl function. It is natural to ask what the form of the vector field Xj is in elliptic coordinates. The answer is that the new equations are quite similar to the old equation, provided that we fix the value of the arbitrary constant alpha, which was used by Jacobi. With this value, alpha is related to the Jacobi to Joachim Stahl integral by this relation. With this agreement, the equation of motion of the vector field J are written here, where now I use a u1 prime, a u2 prime to denote the derivatives of the elliptic coordinates along the vector field Xj. The most surprising outcome here, if you compare the equation, is that the left-hand side of the equations of the vector field Xj coincide exactly with the left-hand side of the equation of the vector field Xh. This occurrence suggests an operation combining the two systems of differential equation into a single system, but not with the time derivative, with the differential of the coordinate. If you just combine with the differential, you obtain this system here. Look, instead of u1 prime, you have du1, u2 prime, du2, etc. Introducing the differential of the elliptic coordinates in place of the time derivative on the left-hand sides, and the differential of the times th and tj along the vector field xh and xj on the right-hand side. The original equations. No, I'm sorry. The original differential equation are recovered by simply expanding the differential of the coordinates in the standard way, and then equating the coefficients of the differential dth and dtj on both sides of the equation. So this is a compact form of two vector fields. The possibility of this packing of the equations of motion of different vector fields into a single system of equations written with the differential of the coordinates instead of their time derivatives is the point that escaped Jacobi's attention. That is the critical point. I call this form the Jacobi form of the equation of motion. Many examples of separable systems have been studied in centuries that divide us from Jacobi, basically following the line traced by Jacobi. The focus was always on writing the equation of motion of a dynamical system in the first Jacobi form, with the time derivative of the coordinates along a single vector field. To my knowledge, little attention has been given to the possibility just shown of writing the equation of motion of a family of commuting dynamical system in the second Jacobi form, with the differential of the coordinates instead of the time derivatives. Breaking away from this tradition, I want to stress in this talk the interest and the simplicity of the second form, the equation of motion shown before. Okay, so now I have my subject, this system of equation. This is the Jacobi form of the equation, and I want to understand the structure of the system. Now I make one step further. I will present just a theoretical interpretation of the result of Jacobi. I think I will present a model of separable system which encompasses that form of the equation. To capture the essence of Jacobi's idea of separable system and of the related Jacobi forms of the equation of motion, it is enough to consider a very elementary geometrical setting. This setting consists of a manifold M of dimension, let's say, M, a family of P vector fields, x1, xp, just the dynamical system, and a family of M minus P function, h1, hm minus P. I emphasize that the manifold is not required to bear any additional geometric structure. In particular, it is not required to be a symplectic or a Poisson manifold. And the function h1, hm minus P are not required to be in evolution. So what means that? that the theory separation of variable is completely decoupled from symplectic mechanics. There's no need. Possibly you need symplectic mechanics to arrive to this setting. But once you have the setting, you can forget. No Poisson bracket, not symplectic form, not involutivity, and so on. It's much simpler than, no, of course, no Hamilton-Jacobi equation, because if you have no symplectic mechanics, you have no Hamilton-Jacobi equation. Where are the assumptions? The vector field are instead required to commute. They are just, and they, and to leave the functions invariant. So you have P commuting vector fields and M minus P integral motion on a manifold dimension M. In this geometrical setting, let F be the foliation whose leaves are the level surfaces of the given functions. We have level. It identifies a special class of coordinates called adapted coordinates. Quite simple. They are defined by equation of the form wilt with the given function. The U are functions you can choose for the moment arbitrarily. The property that character of, sorry, just. Andiamo indietro. The property that characterizes the adapted coordinate is that the first P vectors of the natural frame associated with the new coordinates are tangent to the leaves of F by construction, because so once a system of adapted coordinates has been chosen, whatever system you want, two holonomic frames are defined on each leaf of the foliation F. The frame formed by the given vector field x1, xp, and the frame d over du1, d over dup associated with the adapted coordinates. And now the main idea I will try to transmit to you. The key idea of separability is encoded into the transition matrix connected these two frames. You have this definition. The given vector field x1, xp are said to be separable in the adapted coordinate u1, up if the transition matrix from the frame defined by the given vector fields to the frame defined by the adapted coordinates is a Steckel matrix. In explicit terms, this condition means that the coefficients of the expansion of the vector field d over duj on the basis of the commuting vector fields xk given may depend on all the coordinates of the integral of the motions, h alpha, but only on the corresponding coordinate uj. So there is a decoupling of the adapted coordinates in the transition matrix from the two bases. Okay, I skip a comment. To arrive to the at the Jacobi form of the equations of motions of the vector field x1, xp, it is now sufficient to move from the linkage of vector fields to the linkage of differential forms. This requires to replace the frames with the coframes, the corresponding coframes. So dt1, dt2, which are the times along the vector fields for the coframe of the given vector field, du1, up, the other coframe. Since the coframes are related by the transpose Steckel matrix, one readily gets the equation just by transposing the Steckel matrix. And this is just the Jacobi form of the equations of motions of the P vector fields. They provide the collective Jacobi form of the differential equation of the vector field x1, xp. Thus, the composite of separable system and of Jacobi form of the equation of motion are dual to each other. It's enough to pass from a basis to the cobasis. That's two comments. Oh, sbaglio sempre. The definition of separable system given here is so different from the classical definition of Jacobi, saying that an integrable Hamiltonian system is separable if its Hamilton-Jacobi equation admits a complete integral, which is sum of functions of a single variable. That is the classical definition. That it is justified to ask whether we are talking about the same concept. There is nothing apparently relating the two definitions. To remove this doubt and to highlight one advantage of the new definition, it is worth underlining the following points. First, the class of systems separable according to the present definition is large enough to contain the entire class of Jacobi separable system. In other words, it is possible to show that the class of Hamiltonian systems which are separable in the sense of Jacobi can be embedded into the class of dynamical systems considering the current talk in such a way that they turn out to be separable even with respect to the new definition, using always the same separating coordinates. So nothing of the classical theory is lost adopting the new point of view. On the contrary, something is gained. It is well known there is a problem with the classical theory. It is well known that Jacobi's classical theory is unable to provide a criterion for finding separating coordinates. There is a definition, but you don't know how to find the separating coordinates. They must be guessed and cannot be deduced according to regular procedure. The new point of view, according to which separability is a property that belongs to a family of vector field x1, xp, and not to a single Hamiltonian vector field as in Jacobi, provides instead an explicit rule for the search of separating coordinates. That is a great advantage, in my opinion. It is encapsulated in the so-called Kowalewski separability condition. At this point, it is worth making a brief digression on the theory of separability conditions, because the study of this condition will help us to better understand the geometry that lies behind the theory of separable system. So let me just make this brief digression. Kowalewski separability condition. The most unexpected feature of the new definition of separable system is that it admits a geometric interpretation which avoids the use of any coordinate system. That is, in some sense, paradoxical. You are trying to characterize a specific system of coordinates. I am claiming that this can be done without using coordinates at all. That is something strange. Let me explain this point. The idea leading to such an intrinsic formulation is simple. One traces the coordinate u1, up with the associated tensor field n. We heard about this tensor field yesterday, of type 1, 1, defined by this equation. So it's the tensor field which has the basis as eigenvectors and the coordinates as the eigenvalue. And then one converts the condition on the second matrix into a coupling condition, the vector field x1, xp with the tensor field n, which is very easy. Let's show this new condition. By construction, the noise torsion of n vanishes. Simple. And to this tensor field, and so this tensor field can be used to introduce on each leaf of f a second commutator between vector fields according to the well-known rule, the infinitesimal deformation of the Lie bracket. The new bracket is compatible with the standard one, and therefore you have a pencil of bracket written here, which satisfy the quadratic Jacobi identity for any value of the parameter lambda. So if you accept the definition of the separable system I gave you, you have a pencil of commutators on each leaf of the foliation F. These pencils allow us to intrinsically characterize separable system. There is a brief theorem. The vector field x1, xp are separable in the adapted coordinate u1, up if and only if they commute with respect to the pencil of bracket. Or said in another form, you can say that separable systems are bicommuting. They commute with the standard commutator, and they commute the former commutator induced by separation chord. You can play the two sides simultaneously, or you try the commutator, or you try chord, but that is typical. I will insist on this characterization because it's the basis of my conjecture, final conjecture. Separable systems are bicommuting. That is a completely intrinsic characterization of separable systems. Transforming this result into a set of separability conditions is now a simple affair. It is now to make a change of basis, nothing more. Instead of representing the tensor field n on the frame associated with the separating coordinates, as I done before, we represent it on the frame of the given vector fields as shown by this equation. Just if you introduce the matrix of the components on the given vector basis. The coefficients of phi jk of this expansion are the entries of a matrix phi called the control matrix. It is the main character in the tertiary separating coordinate. It must clearly obey to different set of conditions. The first entails that the Nénot torsion of n vanishes because we started from an operator with Nénot torsion which cancel out. And moreover, as by the above theorem, the commutator xp, xk, or the vector field xj, xk, with respect to the deformed commutator must cancel out. Each of these conditions amounts explicitly to a system of 1/2 p squared p minus 1 differential constraints on the entries of the control matrix, containing both the entries of the matrix and their derivatives along the vector field. So something you can write very easily, explicitly. Solving is a different problem, but to write the separability condition is an easy problem. If one agrees to denote by psi j, the jth row of the control matrix, and by psi j squared, the same row psi squared, one is able to write the above differential constraints in the highly symmetric form written here. That is just a cross derivative. So you derive the row psi k with respect to the vector field k, and you compare with the with the derivative of the row psi j with respect to vector field k, and so they totally they give p squared times p minus 1 condition. These equations are the Kowalewski separability condition. I am almost finished. We are now able to formulate the rule for finding the separating coordinates. Given p commuting vector field x1, xp, and m minus p first integrals on a manifold M of dimension m, equipped with a coordinate system x1, xm, arbitrarily chosen at the beginning, in order to find a system of coordinates u1, up that puts the equation in motion of the vector field simultaneously in Jacobi form, it is required to consider p squared auxiliary unknown function, the entries of the control matrix, and to select such function in such a way to verify the Kowalewski separability condition. Once a particular solution of this condition has been found, the eigenvalues of the control matrix are the separating coordinates of the given vector fields, at least in the region of the manifold where they are function independent. Conversely, any system of separating coordinates are the eigenvalues of a control matrix. In a paper, a new look at the concept of separable system classical mechanics, I have shown that this rule is quite effective to recover in a uniform and regular way some outstanding result obtained by great masters of mechanics of the past. There are some in the literature, some changes, say guess of the separating coordinate, which is very hard. I quote the Kowalewski top for my favorite example, and you can recover independently of the Kowalewski coordinate just by solving this separability condition. Okay, that is a different story. My present purpose is to show that the same rule, the Kowalewski separability condition, is effective also in the study of Soliton equation, which is a different field because are partial differential equation. So far, we have studied dynamical system, but the same technique can be used to study. Okay, my last point. Oh. Claim that in the theory of Gelfand-Dicke equation, there is plenty of examples of separable system of the type considered so far. They arise as a restriction of the flows of the hierarchy on well-chosen finite dimensional invariant manifold. The restriction is necessary because the theory so far is at the level of finite dimensional system, while the Gelfand-Dicke or Soliton equation are on infinite dimensional system. So to match the two theory, you have for the moment to look at finite dimensional restriction. My goal in this second part of the talk is to outline the general mechanism that allows to associate many, in fact, an infinite number of separable systems to any Gelfand-Dicke hierarchy by focuses on the specific example of the Boussinesq equation.
Should it be A2? Not
Sorry?
should it be A2?
I think I3 because both in the A2, A3. So Boussinesq is just the second in the hierarchy, but I call A2.
A2 SL3 is A2. So,
Yeah.
so then it's A2, yes?
I think you are A2. So I'm sorry. Okay. I will correct the misprint. Following an old idea of Bogolianowski and Novikov, I consider the reduction of the Boussinesq hierarchy over the locus of fixed points or the fourth flow hierarchy. Let me draw your attention to two peculiar phenomena that occur in this context. The first phenomenon is the collapse of the hierarchy. This phenomenon manifests itself in the fact that the infinite number of flows of the hierarchy give rise to a finite number of vector fields on the invariant manifold. So you start with a full infinite dimensional hierarchy and you arrive to a finite number of vector fields. And these vector fields, moreover, do not even span the whole invariant manifold. So it's a very teeny part of the invariant manifold. More specifically, the following properties are found in the example under consideration, and the proof is quite easy, because it's not difficult. The locus of fixed points of the fourth flow of the Boussinesq hierarchy is an 8-dimensional manifold. It's life. Each flow of the hierarchy defines a vector field on this manifold. This means that each PDE of the Boussinesq hierarchy gives origin to a system of 8 ODEs on the manifold. Of the infinite sequence of vector fields induced by the hierarchy, only the vector field x1, x2, x5 induced by the flow corresponding to the times T1, T2, T5 of the hierarchy are linearly independent. No more. The remaining vector fields are linear combination of the vector of the previous one. The coefficients of the expansion on the basis x1, x2, x5 are integrals of motion. So you have the vector fields and the integrals. Looks that at the end, the vector field just span a three-dimensional manifold on the 8 dimension. That doesn't cover all the manifold. It's a very interesting phenomenon. The vector field induced by the hierarchy on the invariant manifold commuted in pairs, that is a property which is hereditary. The vector fields induced by the hierarchy admit 5 independent integrated motion. You can compute quite easily and you find. Thus, the collapse of the hierarchy provides us with a manifold of dimension 8, 3 commuting vector fields, and 5 independent integrals of the motion. This is precisely the geometrical setting of the theory separable system formulated above. One can then proceed to search for the separating coordinates, if any, using Kovalevsky separability conditions. So the problem is split into parts. The second phenomenon that occurs in this example is that the collapsed hierarchy is separable. It's not clear why, but indeed it's separable. The notable results here are the 3 vector field x1, x2, x5, which I have not written down explicitly, but it's a simple matter. And the 5 integral the motion, I denote E1, E4, E2, E5, E8, by taking by accounting for some gradation, the green in a certain gradation of the coordinates. It doesn't matter. It's useful for me. It's not important. There are 5 integral of the motion. Define a separable system on the 8-dimensional manifold, the fixed point, the 4th flow of the Boussinesq hierarchy. This means that they verify, define an integral. That's all. What means that? This is a claim. In a coordinate system of 8 coordinates, which is naturally induced by the Boussinesq hierarchy. So you can think that x0 is just one function of the hierarchy. Y0 is the other function. The Boussinesq hierarchy is concerns a pair of functions. Then x1, x2, x3 are just the first, second, and third derivative. So it means that you use just the coordinates in jet bundle associated with the hierarchy. Infinite jet bundles. Okay, so what naturally induced by the Boussinesq hierarchy on the invariant manifold. This matrix, which is very simple, you see, it's just a polynomial, verifies the Kovalevsky separability condition. I must say that this is the simplest solution which verifies some homogeneity condition with respect to certain gradation. It's the computer that compute in very quickly. That is not the difficult part. Verifies the Kovalevsky. Hence, it is a control matrix for the restriction of the Boussinesq hierarchy on the invariant manifold. Okay, once you have the control matrix, you pass to the separating coordinates. Separating coordinates are accordingly the roots of the polynomial equation, just the characteristic polynomial. It's a third order polynomial. It's written here. The coefficients depends on the point, on the coordinates in a reasonable way. There are only two more complicated elements in the control matrix, but the polynomial is written, this is complete. It's just, now comes the more difficult part, namely, you have to compute the second matrix. You know that there exists a second matrix, but the computation of second matrix is not so easy. So I claim that the second matrix associated with the separating coordinates defined above is defined by the following equation. You see, there are the basis, the natural basis associated with the separating coordinates. There are the vector fields. Then we have the second matrix. I just made it multiplied by U1 and so on, just to make, let's say, almost polynomial. This matrix depends on two algebraic functions, phi and psi, of a single variable. And then it's the most interesting part, in my opinion, because it's here where algebraic geometry enters the theory of Soliton equation, from my point of view. The function phi, that is one coefficient of the second matrix, is defined by the polynomial equation written here. It's just, it's not an hyperelliptic curve. It's a trigonal curve, with this name, I'm sorry. It's quite complicated. The coefficients you see is a polynomial in the separating coordinates. It contains the polynomial in the separating coordinates and the integral of the motion. That's just a coefficient. The function, I just finished. The function psi is some. So, last piece. As can be seen from these notes, the separability of the stationary reduction of the Boussinesq hierarchy is a complex phenomenon which requires an in-depth and eccentric treatment. This study clearly goes far beyond the limits of the present discussion. So I stop here, not without first mentioning an open problem. Then it's just last point. Question. Is it accidental that the previous reduction of the Boussinesq hierarchy is separable, or is it the sign of a structural property of the hierarchy? I have no answer, just a suspicion. As we saw before, separable systems are bicommuting, while the Boussinesq hierarchy is bi-Hamiltonian. I believe that these two properties are connected. There are many clues that point to this connection in specific examples, but I don't know abstract argument to support this belief in general. For this reason, I present my belief in the form of a conjecture. Hamiltonian hierarchies are not only integrable, but also separable. That is conjecture. I hope that one in the audience will be able to prove or disprove the conjecture. It's reasonable. Thank you very much.
Questions for Professor Magri?
Yes. Okay, doesn't matter.